We look at the stars every night, yet rarely think about what they are. They seem eternal, fixed points in the sky. But stars are not unchanging. Like us, they are born, they grow, they change, and in time they die. Their lives stretch across millions, even billions of years. Slow beyond our human imagination, yet governed by rhythms of physics, as precise as the ticking of a clock. The story of a star begins in silence, in vast clouds of gas and dust drifting through galaxies. Gravity gathers this material, pulling it tighter and tighter until a spark ignites, nuclear fire. From that moment, a star breathes light into the universe, and from that light, planets form, life begins, and worlds like ours become possible. So tonight, let's follow the path of a star's life, from its fragile beginnings to its luminous middle years, to its spectacular and sometimes violent end. And along the way, we'll remember that the atoms within us, the iron in our blood, the calcium in our bones, were once created inside stars long gone. This is the life of a star. Stars begin their lives in places that seem at first glance empty. When we look into the night sky, much of the space between the bright points of light appears dark, almost vacant, but hidden in that darkness are enormous clouds of gas and dust, stretching across dozens, even hundreds of light years. These are nebulae, stellar nurseries, where new suns are quietly forming. Nebulae are not uniform. Some glow with faint colours, illuminated by nearby stars. Others are cold and opaque, hiding what lies within. They are composed primarily of hydrogen, the simplest and most abundant element in the universe, with smaller amounts of helium and trace amounts of heavier elements. For millions of years, the gas and dust drift in slow motion, tugged gently by gravity. The process is patient, but given enough time, the invisible pull of gravity begins to collect the material into denser clumps. As these clumps grow, they attract more matter, their gravity increasing as their mass accumulates. Within these dense regions, called molecular clouds, temperatures fall and pressure rises. Dust particles shield the gas inside from starlight, allowing it to cool, making it easier for gravity to continue its collapse. What begins as a faint disturbance in a vast cloud can become the seed of a new star. Eventually, one of these dense clumps contracts until its center becomes hot and pressurized. At this stage, it is called a protostar. The protostar is not yet shining like a true star. It is still gathering material, pulling in gas from its surroundings. Around it, disks of dust and gas begin to swirl, flattening into a rotating system that may one day give rise to planets. The protostar grows hotter, glowing faintly in the infrared, invisible to our eyes but detectable with special instruments. Inside, the pressure of gravity continues to squeeze atoms together. The temperature in the core rises to millions of degrees. At around 10 million degrees Celsius, a profound transformation occurs. Hydrogen nuclei, protons, begin to fuse into helium. In this fusion process, a small fraction of mass is converted into energy, released as light and heat. This is the moment of ignition, when a star truly comes alive. The star's light pushes outward, countering the inward crush of gravity. The balance between these two forces, gravity pulling in, radiation pushing out, is what allows a star to shine steadily. From here, the star will settle into the longest phase of its life, the main sequence. But in its earliest days, as a newborn star, the universe is already changed. A source of light has joined the sky. The story of how we came to understand this process is as fascinating as the stars themselves. In the 18th century, astronomers like William Herschel began to systematically observe the hazy patches in the heavens. With the telescopes of his time, Herschel catalogued hundreds of nebulae and clusters, noting their shapes and brightness. He speculated about their nature, unsure whether they were collections of stars too distant to resolve or clouds of luminous matter. His observations marked a turning point. Nebulae were not just imperfections in the glass of the telescope or tricks of the eye, they were real structures in space. In the 19th century, advances in spectroscopy revealed even more. Astronomers learned that nebulae contained hydrogen and other gases, that they were physical objects, not mere smudges on the lens. The realization grew that these were not just passive features of the sky, but the cradles of creation, places where new stars were being born. Today, with instruments like the Hubble Space Telescope and the James Webb Space Telescope, we can peer into these nurseries with astonishing clarity. Images of the Eagle Nebula's pillars of creation, or the Orion Nebula's glowing clouds, show us what Herschel could only imagine. Stars in the very act of being born, surrounded by clouds of dust, some already shaping young planetary systems. From the cold emptiness of interstellar space, gravity forges fire. The quiet gathering of gas becomes brilliance, and from that brilliance, entire worlds may one day take form. Once a star has ignited its nuclear furnace, it settles into the long, steady rhythm of its life. This stage is called the main sequence, a phrase coined in the early 20th century when astronomers began plotting stars by their brightness and colour. On this diagram, known as the Hertzsprung-Russell diagram, most stars formed a clear, continuous band. That band was the main sequence, the realm where stars spend the vast majority of their lifetimes. On the main sequence, a delicate balance holds steady. Gravity pulls inward with immense force, trying to collapse the star. At the same time, energy released from nuclear fusion pushes outward. In the core, hydrogen is fused into helium, releasing light, heat, and neutrinos. That light radiates outward, travelling through the star's layers before escaping into space. The balance between inward gravity and outward radiation is called hydrostatic equilibrium. It is this equilibrium that allows a star to shine consistently for billions of years. But not all stars are created equal. The role of mass is decisive. A star's mass, set at birth by the amount of material gathered from its nebula, determines everything about its future. Massive stars burn through their fuel quickly. Their cores reach higher pressures and temperatures, fusing hydrogen into helium at a furious rate. As a result, they shine brighter, hotter and bluer than smaller stars, but their lives are short, measured in only millions of years. By contrast, small stars, such as red dwarfs, sip their fuel slowly. They glow faintly in shades of orange or red, and though they may be dim, they are the universe's true survivors, living for trillions of years, far longer than the current age of the cosmos. Our own sun sits comfortably in the middle. With a mass about 330,000 times that of Earth, it is neither the faintest dwarf nor the most brilliant giant. It shines with a steady yellow-white light, converting around 600 million tons of hydrogen into helium every second. Yet, despite this enormous rate, the Sun has enough fuel to last for roughly 10 billion years. Right now, at about 4.6 billion years old, it is just past middle age, mature, stable, and dependable. For Earth, that stability has been a gift. Without the Sun's consistent light and warmth, life could not have taken hold. Understanding what powered the sun was once one of the greatest puzzles of science. For centuries, thinkers speculated. Some believed stars might burn like giant fires, consuming fuel. But this made little sense. A fire the size of the sun would exhaust itself in a few thousand years, far too short compared to the geological age of Earth. In the late 19th century, others proposed that gravitational contraction, the slow collapse of the sun under its own weight, released energy. This could keep it shining for millions of years, but again, not long enough. The true answer came only with the discovery of nuclear physics in the early 20th century. The English astrophysicist Arthur Eddington was among the first to realise that the sun's energy came from the fusion of hydrogen into helium. In the 1920s, he boldly proposed that mass could be transformed into energy, invoking Einstein's famous equation E equals mc squared. At the time, this idea was almost shocking, but Eddington insisted it was the only explanation consistent with the sun's longevity. His insight laid the foundation for modern stellar astrophysics. Even more revolutionary was the work of Cecilia Payne, a young astronomer in the 1920s who studied the light from stars using spectroscopy. By analysing absorption lines in stellar spectra, Payne concluded that stars were made primarily of hydrogen and helium. This went against the prevailing belief that stars had a composition similar to Earth. At first, her conclusion was dismissed, but with time, it was proven correct, and her discovery reshaped our understanding of the universe. The stars were not like us. Instead, we were made possible by them. So, on the main sequence, a star's adulthood unfolds. Some blaze briefly and perish young. Others, like our sun, burn steadily for billions of years. And the smallest, dimmest stars may outlive every galaxy we see today. Mass is destiny. From the moment a star is born, its weight writes the script of its life, setting the pace for how it will shine and how it will someday fade. When we gaze at the night sky, the stars may seem alike, small white dots scattered on a dark canvas. Yet in truth, they vary enormously. Some are vast and luminous, blazing millions of times brighter than the sun. Others are faint red embers, glowing with such little light that even the nearest among them are invisible without a telescope. The universe is a gallery of stellar diversity. Among the smallest are red dwarfs. These stars make up the majority of stars in the Milky Way. Though few are visible to the naked eye, they are small, often less than half the sun's mass, and burn their hydrogen slowly. Their dim, reddish glow is steady, and their lives stretch into trillions of years, so long that not a single red dwarf has yet lived out its full span since the universe began. At the other extreme are the giants and supergiants. These stars swell to hundreds of times the sun's diameter. Betelgeuse, the red supergiant in Orion, is so large that if it were placed at the centre of our solar system, it would extend past the orbit of Mars. Such stars are luminous beacons, visible across vast distances. But their brilliance comes at a cost. They live brief, turbulent lives, destined for spectacular ends as supernovae. Some stars vary unpredictably. Variable stars change their brightness over days or weeks. In some, like Cepheid variables, the fluctuations follow a regular rhythm caused by pulsations in their outer layers. These stars became crucial in astronomy. By studying their periods, Henrietta Swan Leavitt discovered a relationship between brightness and pulsation, providing astronomers with a cosmic yardstick to measure distances across galaxies. To bring order to this diversity, astronomers developed tools of classification. One of the most important was the Hertzsprung-Russell diagram, introduced in the early 20th century by Einar Hertzsprung and Henry Norris Russell. This diagram plotted stars by their luminosity and their surface temperature, which corresponds to colour. Suddenly, patterns emerged, the main sequence stretching diagonally, the giants above, the white dwarfs below. The diagram became a map of stellar evolution, showing not just what stars are, but how they change over time. But to create such a diagram, astronomers first needed reliable ways to measure stars. One of the oldest methods was parallax, the apparent shift of a nearby star against the background of distant stars as Earth moves around the Sun. In 1838, Friedrich Bessel made the first successful measurement of a stellar parallax, proving that stars lay at vast, measurable distances. His work opened the way for precise mapping of the cosmos. Another tool was spectroscopy, the study of light split into its component colours. By examining a star's spectrum, astronomers could determine its temperature, chemical composition, and even motion. In the late 19th and early 20th centuries, the Harvard College Observatory employed women known as computers to classify hundreds of thousands of stellar spectra. Annie Jump Cannon, one of the most prominent, developed the system still in use today, the OBAFGKM sequence, arranging stars by temperature from hot blue O-type stars to cool red M-type stars. These advances transformed stars from distant points of mystery into physical objects with measurable properties. A star could be placed on a chart, its temperature known, its distance measured, its composition revealed. The night sky became not just a collection of lights, but a structured system with rules, categories, and histories. And yet, for all the order we impose, the variations remain dazzling. Stars are not only suns like ours, but also dwarfs barely glowing, giants swollen to unimaginable size, pulsating variables marking cosmic distances, and white dwarfs glowing with the faint heat of their dying cores. Each point of light overhead is not just a dot, but a story, a stage in a life vastly longer and stranger than our own. No star can burn forever. Even the most steady and long-lived must one day face the limits of its fuel. For ordinary stars, those with masses like our Sun or smaller, the end is not a violent cataclysm, but a slower, more graceful decline. Their lives stretch across billions of years, yet eventually the hydrogen in their cores is consumed. And when the balance between gravity and nuclear fire falters, change begins. During the main sequence, hydrogen fusion in the core creates helium, building up slowly over time. Eventually, the hydrogen in the very centre is exhausted. Fusion ceases in the core, and without that outward pressure, gravity takes the upper hand. The core contracts, squeezing tighter and growing hotter. Around it, a shell of hydrogen remains, and under the new pressure, this shell begins fusing even more intensely than the core once did. The star responds by expanding outward. Its outer layers swell, cooling as they stretch, and the star becomes a red giant. For the Sun, this stage will arrive about 5 billion years from now. As it swells, it may grow so large that it engulfs Mercury and Venus, and perhaps even Earth. From our perspective, the Sun will appear vast and ruddy in the sky, a swollen giant blazing with unstable energy. Inside, as the core contracts further, temperatures rise high enough to ignite a new form of fusion. Helium, the ash of hydrogen burning, begins to fuse into carbon and oxygen. This stage is shorter and less efficient, lasting only a fraction of the star's life. In smaller stars, the process may stop there, but in slightly larger ones, helium fusion continues in pulses, further destabilizing the outer layers. The end of this phase is marked by beauty. The outer layers of the star, no longer tightly bound, are pushed away into space. They drift outward, forming a glowing shell of gas known as a planetary nebula. The name is misleading, given by early astronomers who saw these circular patches through telescopes and thought they resembled planets. In truth, planetary nebulae are the luminous shrouds of dying stars, glowing in soft blues, greens and reds as ultraviolet light from the exposed core ionizes the gas. The Ring Nebula in Lyra or the Helix Nebula in Aquarius are haunting reminders of this final transformation. At the center of these shells remains the exposed stellar core, a white dwarf. This is the last ember of the star, composed mostly of carbon and oxygen, packed into a sphere no larger than Earth, yet containing a mass comparable to the Sun's. The material inside a white dwarf is extraordinary. Electrons are squeezed so tightly that quantum mechanics provides the pressure to resist further collapse. This degenerate matter is unlike anything we know on Earth. White dwarfs no longer fuse elements. Their light comes only from residual heat, slowly radiating away over billions of years. At first, they glow white hot, with surface temperatures of tens of thousands of degrees. Over immense spans of time, they cool, fading through shades of yellow, red, and eventually into darkness. Theoretically, after trillions of years, they will become black dwarfs, cold, invisible relics. But the universe is not yet old enough for any white dwarf to have reached that final stage. All still glow faintly in the dark. Our own sun will follow this quiet path. In about 5 billion years, it will expand into a red giant, casting off its outer layers. Its core will shrink into a white dwarf, glowing in the center of a planetary nebula. Eventually, the nebula will disperse into space, enriching the galaxy with carbon, oxygen, and other elements forged in the sun's interior. That material may seed new stars, new planets, perhaps even new forms of life. The sun's death will not be an end, but a continuation of the cycle that has always governed the cosmos. This cycle reveals something profound. The ordinary stars, though they fade gently, are cosmic alchemists. They forge elements in their hearts and release them into the universe. Without their deaths, there would be no carbon in our cells, no oxygen in our lungs, no iron in our blood. Every breath we take is possible because stars lived, shone, and eventually died. The fading of a star is both melancholy and beautiful. To human eyes, it feels like loss, a great light dimming, a sun extinguished. But to the universe, it is creation. Each white dwarf is a silent monument to the immense forces of nature, cooling slowly in the cosmic night, waiting out ages far longer than all of recorded history. And every planetary nebula is a glowing reminder that from endings come new beginnings, and from the ashes of one star, countless new worlds may someday rise. For massive stars, the end is far less gentle than the quiet fading of a white dwarf. When stars, many times the mass of our sun, exhaust their fuel, they meet their fate in spectacular, violent events that reshape galaxies. These colossal deaths are not only destructive, they are also creative, forging the heavy elements that make planets, oceans, and life possible. A massive star burns furiously throughout its life, consuming hydrogen quickly and progressing to fuse heavier elements. In its core, helium becomes carbon, then oxygen, then neon, magnesium, silicon, and finally iron. But here the chain halts. Iron cannot release energy through fusion. Instead, it absorbs it. Once iron builds up in the core, fusion ceases, and the delicate balance between outward radiation and inward gravity collapses. The core implodes in an instant, falling inward at a significant fraction of the speed of light. Outer layers crash down, then rebound violently. The result is a supernova, one of the most powerful explosions in the universe. In a single moment, a supernova can outshine an entire galaxy, releasing more energy than the Sun will emit in its entire lifetime. These cataclysms scatter the star's outer material into space, enriching the cosmos with elements heavier than iron: gold, uranium, iodine. Every atom of precious metal on Earth, every trace element essential for biology, was forged in the deaths of massive stars. What remains behind depends on the mass of the collapsed core. For stars of intermediate mass, the collapse crushes protons and electrons together, creating a city-sized sphere of neutrons. This remnant is called a neutron star. Despite being only about 20 kilometers across, a neutron star can contain more mass than the Sun. The density is unimaginable. A teaspoon of neutron star matter would weigh billions of tons. Neutron stars can spin rapidly, their intense magnetic fields producing beams of radiation. If these beams sweep past Earth, we observe them as pulsars, rhythmic signals flashing with clock-like precision. In 1967, a graduate student named Jocelyn Bell Burnell discovered the first pulsar, detecting an unusual, repeating radio signal. At first, she and her advisor even nicknamed it LGM, for Little Green Men, joking about extraterrestrial origins. But the truth was even more remarkable. She had found the signature of an entirely new class of celestial object. Her discovery revolutionized astrophysics, revealing the extreme states of matter hidden in collapsed stars. For the most massive stars of all, even neutron stars cannot withstand gravity's pull. If the core exceeds a certain threshold, known as the Chandrasekhar limit, calculated in the 1930s by the Indian physicist Subramanian Chandrasekhar, collapse becomes unstoppable. Space and time themselves warp inward, creating a black hole. A black hole is defined not by what it is, but by what it hides. Its boundary, the event horizon, marks the point beyond which nothing can escape, not even light. Inside, the mathematics of general relativity predict a singularity, a place where density becomes infinite and our physical theories break down. Around this invisible sphere, gravity is so intense that time slows, space curves, and light is bent into strange arcs. We cannot see inside, but we can observe the effects. Stars whipping around unseen companions, gas spiralling inward in luminous disks, jets of radiation shooting across interstellar space. The study of black holes has become one of the most active fields in astrophysics. From the first theoretical calculations by Chandrasekhar and others, to the detection of gravitational waves from black hole mergers in 2015, to the Event Horizon Telescope's image of the supermassive black hole in galaxy M87, each step has brought us closer to understanding these cosmic mysteries. Massive stars then die in fire and violence, but their legacies endure. Supernovae scatter the building blocks of life across space. Neutron stars stand as monuments to the extremes of matter. Black holes mark the edge of our knowledge, where physics meets its limits. From the deaths of massive stars, galaxies are enriched, new stars are seeded, and life becomes possible. Their endings are not final, but transformative, echoes of creation written in light, in gold, and in the very atoms of our bodies. Every atom in our bodies has a history, the oxygen we breathe, the calcium in our bones, the iron in our blood, none of these elements were present in the newborn universe. In the beginning there was only hydrogen, helium, and traces of lithium. The heavier elements, everything that makes planets and people possible, were forged later inside stars. Through nuclear fusion, stars transmute the simplest atoms into more complex ones. In their steady main sequence lives, they fuse hydrogen into helium and helium into carbon and oxygen. In their final stages, massive stars forge even heavier elements in their cores, before scattering them across the cosmos in brilliant supernovae. Each cycle of stellar birth and death enriches the interstellar medium, seeding new generations of stars with the raw materials for planets, oceans, and life. It is not a metaphor, but a literal fact. We are stardust. The atoms in our bodies were once fused in the hearts of stars that lived and died long before the sun was born. When Carl Sagan said, "We are made of star stuff," he gave voice to this scientific truth in language that resonates beyond equations. It is science and poetry together, a reminder that the universe is not only something we observe, but something we belong to. The recognition of this connection changes how we see ourselves. We are not separate from the cosmos, we are its continuation. The elements that flow through our veins were once scattered through interstellar clouds, drifted for eons, gathered into a star and its planets, and eventually became part of the long story of life on Earth. To look up at the stars is, in a sense, to look back at our own origins. This perspective invites reflection on cycles. Stars are born, they live, and they die, but their endings give rise to beginnings elsewhere. The death of one star enriches the galaxy for the birth of many more. Permanence is an illusion, impermanence is the law of the cosmos. And yet, within that impermanence lies continuity, a chain unbroken across billions of years. For human beings whose lives are brief compared to the lifetimes of stars, this can feel humbling. We exist for a moment, like sparks against the backdrop of cosmic time, and yet, in that moment, we carry the universe within us. The cycles of the stars are mirrored in our own cycles: birth, growth, decline, and return to the elements. Just as stars return their matter to the galaxy, we too return our matter to Earth, becoming part of the soil, the air, and the life that follows us. This duality, impermanence, and continuity is one of the profound lessons of astronomy. The stars remind us that nothing lasts forever, but nothing is wasted. The universe recycles, transforms, and renews itself endlessly. From ashes come new lights, from endings come beginnings. When we sit beneath the night sky, we are not simply spectators of distant points of light. We are participants in the same story. Our atoms were kindled in stars, our planet was shaped by their remnants, and our existence depends on the quiet generosity of suns long gone. To reflect on this is to feel both small and vast at once, fleeting and yet inseparably bound to the eternal rhythm of the cosmos. The story of stars is, in many ways, the story of light itself. For billions of years, the universe has been illuminated by their fire. But fire has limits, and so too do the stars. Though their lives may span unimaginable ages, the cosmos itself looks ahead to a time when stars will no longer be born, and the great age of starlight will come to an end. Stars form when gravity gathers gas and dust into new suns. Yet with each generation, more of this raw material becomes locked away in remnants: white dwarfs, neutron stars, and black holes. Supernovae recycle some matter, but much of it is hidden from further use. Already astronomers observe that galaxies are forming fewer stars than they once did. Billions of years from now, the stellar nurseries will fall silent. No new suns will rise. The fate of the universe then belongs to the smallest stars. Red dwarfs, the faint, cool majority, burn their hydrogen slowly and thoroughly. While massive stars live only millions of years, red dwarfs endure for trillions. These dim embers will be the last lights burning in the cosmic dark. But even their patience has a limit. When a red dwarf finally runs out of fuel, it fades into a white dwarf, cooling over eons into darkness. These remnants, known as black dwarfs, have never yet existed. The universe is still too young, but in the far future they will fill the galaxies, silent echoes of once brilliant suns. The cosmos then enters the degenerate era, dominated by stellar corpses. White dwarfs, neutron stars, and black holes drift endlessly through expanding space. Rare collisions may still produce brief sparks of light, but the steady glow of starlight will be gone. Even black holes are not eternal. Stephen Hawking showed that they can evaporate over unimaginable spans of time through what is now called Hawking radiation. The largest may take 10 to the 100 years to disappear, a number so vast it slips past human comprehension. Eventually, the universe approaches what physicists call the heat death. All matter and energy are evenly spread, all gradients erased. No fuel remains for stars or galaxies. No processes persist to create structure. The cosmos continues to expand, but it is silent, dark, and cold. And yet there is an image worth holding, the final star. Perhaps a lone red dwarf in some forgotten corner of a galaxy, long dissolved, burning faintly for trillions of years. Its light falls on barren worlds, its glow resisting the darkness for as long as it can. And then, at last, it too fades. The universe enters eternal night. To imagine this is not despair, but perspective. Nothing, not even stars, lasts forever, yet their endings gave us everything. The elements of our bodies, the warmth of our sun, the chance for life. Their story, even in silence, continues in us. And so the stars live, and the stars fade. From the quiet collapse of nebulae to the long glow of red dwarfs, to the final hush of black dwarfs and the distant whisper of heat death, the story of light has its beginning and its end. But within that story lies a gift. The atoms that make us, the iron in our blood, the oxygen in our breath, the carbon in every living cell, were born in stars that lived long before us. Their brilliance continues through us and through every living thing. When you look up at the night sky, you are not just looking outward, you are also looking inward into your own origins. The stars are your ancestors, their story is yours. So rest now, knowing you are part of this cosmic rhythm, brief, beautiful and eternal in its continuity.